speaker is coming from the Technical University of Eindhoven. It is Professor Jos Brouwers, who will have an online presentation. So unfortunately, he could not make it to be here today. Mr. Brouwers has a master degree in mechanical engineering from the Eindhoven University of Technology, a PhD degree in technical sciences, also from the Eindhoven University. And since 2009, he's a full professor for building materials in the Department of the Built Environment. His major field of interests are building materials and sustainable building. And he will give us some more insights about the structural applications of UHPC. So, welcome, Mr. Brouwers.
Okay. Well, thank you for this kind introduction. Indeed, I cannot attend this meeting because later this afternoon, actually in half an hour, a PhD defense will start here in Eindhoven, where I cannot be absent. Otherwise, I would have loved to be at your interesting meeting. I will talk as introduced. I will talk about more constructive applications of UHPFRC. And we have seen some architectural applications and where you can make use of slender elements and so on. But here I will talk about another aspect of UHPFRC, and that is its protective properties. And this research was done by PhD students Lee, Zhao, you see them here, and they were supervised by Dr. Yu and me. The PhD thesis from Lee and Zhao, you can also find online on my website. I will show you the link later. So now the PowerPoint is reacting slowly, but let's see. Well, I will start with a small introduction, then I will tell you about how we do the material design of the UHPFRC. I will show you how we did some low velocity impacts, also high velocity impacts with bullet, and I will conclude with some conclusions. So why ultra high performance concrete? Well, some structures are subjected to sometimes unexpected impact loadings, for instance, in terrorist attacks or accidental collisions. And here we see some examples, war, terrorist attack, and also simply vehicle collision or ship collision or whatever. And why UHPFRC is a good candidate to be used in such conditions. Well, the high compressor strength, tensile strength, the energy absorption capacity is an important one, and the damage tolerance. But we've seen it also in the presentations of today. Fibers are needed. We used mostly steel fibers. That makes the material more expensive, and also the environmental impact is negatively influenced. Also, a lot of cement is usually used, also not so favorable from cost and ecological point of view. So we looked at how we can save on these elements, and it starts. I go in the opposite direction. I start on the right. We looked at how to use it in the structure. So we work with layered structures where fibers are applied in some parts and some parts not. The dosage we optimized. We looked critically at from how much steel fiber dosage is needed. Then we introduce coarse aggregates, because if you introduce more and coarse aggregates, less fines are needed. And if you look at the fines, we looked at how much of the fines we could substitute by fillers. So all these measures help in reducing steel and cement. Well, when we look at here, you see already a layered structure where we have a layer with 0 fibers, we have a layer with 2% fibers, where the tensile forces are, the fractional tensile forces are taking place. We use aggregates. Well, the aggregates must also be of high strength. Of course, you cannot use quartz aggregates. So we use basalt aggregates for these ultra high performance concretes. And we use them in all kinds of gradations. And here you can see the sand size, 1 to 3 millimeter. But we even went to 16 to 25 millimeter aggregates. Well, when you use all these different size classes, you need to proportion them in the right way. And we have our own mix design software that we also use for, let's say, normal concrete. but also for this concrete, where we apply many different sizes, not only fines, cement and filler and nanosilica and so on, but also coarse aggregates, you need to do a good particle design. Mix design. So here you can see some particles that we use, including the particle size distributions. This is micrometer. Here you can see 10,000 micrometer. That's 10 millimeter. Well, we go beyond, you can see here. And here we have the fines particles that are in the range of 1 micrometer to 100 micrometer, typical cement range, for instance. And all these particles, this is a logarithmic scale. So these are huge size differences in relative terms. We use some microsilica, we tried that, also nanosilica, but we minimized it. We saw already in earlier talks that microsilica was completely abandoned or also minimized because of its high price, availability, but also the shrinkage it caused. We use different plasticizers, also plasticizers that are still in the research phase from companies like Sika, for instance, we got them. We use a number, we also compare the number of fibers, hooked fibers of different lengths, but also straight fibers, 30 millimeter. So here you can see some preliminary researches. We looked at the effect of SP dosage on flowability. So you can see that different SPs have different saturation points, that further addition does not help in spread anymore. We looked at the effect on hydration, there's calorimetric results, and also after mixing and so on. Considering the time, I will not go into details. We also look at limestone as a candidate for cement substitution, and you can see we in the flow experiments, we look at the SP dosage, and we also did test with zero cement to look at what limestone powder is doing in a spread flow test with as function of SP dosage. And you can see that the SP also interacts with the limestone. This is 0% limestone, and here we can see 100% cement, and you can see the mixes. Well, we also look at CSH formation, how much CSH do we have, and by mass on binder and also on mass of UHPFRC. And also here we can see the effect of more limestone powder and less cement. Here is an interesting one. I cannot go into details in all these slides, but here we can see that at 50% limestone powder, it seems like a maximum amount or an optimum dosage, that there the strength is highest. So we can go up to 50% limestone powder in this mix and have the same strength. Here you can see the binder efficiency. That is actually the strength that you get per kilo of cement. Well, the cement is reduced because we have more limestone powder, so there's less cement, but the strength that the cement is providing is more. But it has to do with that it has the chance to react more completely, which is very interesting. And you can see then also the binder efficiency, which is megapascals per kilogram of cement per cubic meter, and that also rises when you reduce the cement and increase limestone powder. Well, that's the fine part, the binder part, where we included limestone powder in the binder. Well, then we looked at the aggregates to introduce them in the mix, because that also helps in saving the fines in the mix. And normally coarse aggregates are, you will not find in UHPFRC. We saw it also in the previous presentations, which were mostly about paste, as we can call it, because there were no aggregates in it, or at most you can talk about mortar when 1 to 3 millimeter or 4 millimeter aggregates are included, but that's it. Well, we went higher, above this 2 or 4 millimeter, and we see that there's a limited strength loss. I will show you some details when we have proper packing of the granular constituents. And it has savings when you are able to include coarse aggregates. Shrinkage will be reduced, also creep. We have material savings and cost, and also the impact resistant is not negatively affected, even positively affected, as you will see. Well, here we can see some effects. You can see some mixes where the maximum size was 3 millimeter, 8 millimeter, 60 millimeter, using the same mixed design method. And you can see when we increase the particle size that there's no negative effect on compressive strength and tensile splitting strength. So that's already quite promising. Also the powder content that decreases then, there's less powder needed when you have more aggregates in your mix. And we saw, we could reduce by increasing this aggregate content, aggregate size, and aggregate content, that the powder demand, we could reduce it from 900 kilograms to 700 kilograms. And the 700 kilograms, as we have seen, consist, let's say, for half of cement only. So actually we are making a high performance concrete with quite normal cement contents already, which is very interesting, I think. Let's see what the next slide. Well, what I also mentioned is besides the material design, also the plate design or the beam design is important. And for that we looked at multi-layered technology, so to cast in layers. The PowerPoint is not reacting, I'm sorry. Oh, there it is. So because the steel fibers are especially needed in the flexural zone, not so much in the compressor zone. And so that's the reason we looked at 2 and even 3 layered structures. In the back layer, fibers are needed. And in the front layer, when you have impact of a projectile, a bullet, for instance, also some fibers can be desired, but less than in the back layer. But so that's the reason we also looked at 3 layered designs. Well, we also modeled it. We simply by using beam theory. Then you let your beam consist of 2 materials, each with their own elastic modulus, and we did some preliminary calculations from what, and solving analytically these equations from how. When you have two types of beams connected, which each have different properties caused by different steel fractions, how the beam will behave as an integrated as this 2 beam system. And we found already that the layer ratio, when that is around 0.6 or whatever in that range, that is optimum. That means that actually more or less half of the beam you don't need to reinforce with fibers, and the other half with fibers to obtain the same properties as when you mix the fibers throughout the whole beam. So that saves already in the efficiency. I will show you results later from these layer beams, from 1 layer beams, so homogeneous beams, but also 2 and 3 layer beams. Well, we did some here a little bit the information about the test methods that we did, the dynamic test methods. We also did, of course, static test impacts, but they are not so spectacular. We know them all. And this is a so-called pendulum impact test. It's 2 frames which are not connected with each other. We have a concrete sample hanging here, a beam, and then with a hammer, we let it collide and we look how far they go, and also after how many, here you can see it, and after how many punches the concrete will be damaged, broken. This was a setup that was developed with late Ad Verhagen. His name was mentioned also by Peter Buitelaar. He advised us in this research throughout the past years. And this is typically a setup that he liked a lot and that we also adopted at the university. And then with a high-speed camera, you can see we monitor what is happening in the beam. So we have results of that. We also did, there's also low velocity. We used drop weight impact. You can see it here. Here is the ball with an electromagnet. Well, when you switch off the current, then the ball will fall. It's 2.5 meters. And we hit here, on top of this hammer, we hit the beam and we measure the response of the UHPFRC beam. And then we looked at the impact number and the absorbed energy before the material collapses. Then as last test, we did a high velocity penetration test. Also, we did it at the end because we have limited access to these tests. Of course, we only had a few days or perhaps a week in total. And it was not in our own lab. This was done by the Dutch Army. We went there and they, with our concrete, and they performed the test with this bullet, the 7.62 millimeter bullet. Later, they also did with bigger bullets. I don't have in this presentation. And later, they even tested in Germany with grenades, but that is classified information. And with also with 2 penetration velocities. And here you can see already a sample that has been hit by such a bullet. Well, here you can see also with high-speed camera, you can see how it impacts. It goes quite slow, the connection or the power point is slow, but the bullet should come from the right. And then we looked at the damage of the concrete samples. We looked at the crater, we look at the rear, the scabbing, also very important, because that can also hurt people, the pieces that are, the shrapnels that are made loose from the concrete and splash into the space that should offer protection. And here we can see the measure of penetration here. It's a pity that the bullet is not working. Well, I'll try one more time. And you can see that's coming, yeah. So this is what we measured with the high-speed camera. Okay, well, there are already empirical tests already from the 60s from how a certain projectile and a certain concrete quality, if a certain projectile with a certain diameter, speed, mass, and so on impacts concrete. There were already semi-empirical formulas for that in the literature and in books, but not for this ultra-high performance concrete. So based on the results that we had, we extended this formula to also be able to design concretes with high speed, with ultra-high strength. How the response will be to a certain projectile. So we used an existing formula and we adjusted it we made it possible that with this formula also high strength concretes can be calculated, the impact effect. Well, here you can see some effects. Here you can see steel fiber volume, also important to control. And here you can see the compressive strength and the splitting tensile strength. And you can also see the straight fiber and the hooked fiber, and perhaps unexpected. Perhaps it's not what you would expect, but the straight fibers performed the same or even a little better, the short straight fibers, than the 30 millimeter hooked end fibers. And here you can see the effect of steel fiber volume on impact, how deep the bullet penetrates, the depth of penetration, DOP. And you can see that when there's no steel fibers, then it penetrates 80 millimeter or even more. But as soon as you add steel fibers, you can see already with 1%, then it is reduced to 60 millimeters. And you can also see that beyond 1, let's say 2 millimeters, further steel addition has not much use anymore. So I think we continued mostly with 1% steel, which is quite low actually for these purposes. Well, here we can see the effect. This is the bullet test, the high velocity. You can see how it looks like. Here we have 0 fibers. Well, then the plate simply is destroyed in one go. And you can also see here, the 0, the 1%, the 2%, and the 5%. But you can see already that beyond 1%, not much improvement is seen anymore. Here, in effect, next slide is. I have to wait till the. Yeah, here we can see the maximum aggregate size. And you can see already also here the compressive strength is this again, simply compressive strength and tensile splitting strength. That with our mixed design, we can go that the aggregate size does not makes much difference anymore, and that it also results in a powder content decrease, so cement and limestone powder and so on, from 900 to 700 kilograms. I mentioned that before already. And here we can see also the depth of penetration, which actually is lower with bigger aggregate size. So the strength statically is almost the same, but dynamically with the bullet, with 2 speeds, you can see the speeds here and also the depth of penetration. You can also see the effect of a speed increase from 840 to a little bit more than 900 meter per second. There you have already quite a big increase in penetration depth. But you can also see here that with increasing aggregate size, the depth of penetration is reduced. So very nice result. And here you can see the effect of penetration on slab depth. So how thick is your sample? And here you can see again for the 2 speeds again, 900 and 800 meters per second. Well, when the slab thickness is thinner than the depth of penetration, the bullet passes through, that we see here. But at some point, the bullet will be stuck, will be stopped by the concrete. And then here you can see we need about 80 millimeters for 900 meters per second. But you can also see that when the slab thickness increases further, the bullet penetrates less deep. And also here we see that effect. So when you have a little bit more excess thickness, the bullet will actually penetrate less deep. Well, here you can see the effect of target thickness under the same conditions. You can see with 8 millimeter the damage, 90 millimeter 100, and with 110, here you see no spalling at the backside already, which is very good, because this is not what you want, because then you still have damage on the inside and danger at the inside. Well, here a little bit information about the multi-layer research that we did. We look at 830 millimeter per second. That here you can see the target size. And we had double and triple layered UHPFRC, so to study the aggregate size and the fiber amount. Well, we use a single layered concrete. Here you can see that the 8 means 8 millimeter maximum aggregate size, 1 means 1% steel fiber, and this is 90 millimeter. And here you can see with 2 layers, so 8 millimeter aggregates, 1 steel fiber, and here 60 millimeter aggregates, also 1% steel fiber. And here we have 3, the second one double layer, 16 now on the outside and 8 millimeter on the other side. And well, here we can see when the large aggregates are at the impact layers, so where not the flexural forces are, that the reduction is better. That's also what you would expect, perhaps. So you would, it's better to have the coarse aggregates on the impact side. Here we also have some results. Here we have single layer, again 90 millimeter, 8 millimeter maximum aggregate size. Here we have a triple system with 8, 1.5 steel, 0 steel in the middle, 30 millimeter, and then 1.5 in an outer layer. So the total steel content is the same, but now part is redistributed to the inner and the outer layers. And here again another recipe. And also there we saw that this is favorable. It is a little bit more work because you have to cast the concrete slab or beam or whatever in layers, but it's not undoable. And then you benefit from the properties. So it's more, let's summarize the conclusions. Well, we managed to make a low cement UHPFRC by substituting cement by limestone powder, for instance, and also reducing the silica content. The total powders as such we could reduce by coarse aggregated UHPFRC by adding these coarse aggregates that reduce the powder content and then also the cement content. Also, the steel fiber is optimized. Well, here 1.5 to 2% seems to be optimum. Well, I dare to say that 1% could be good already with steel fiber. And then, when you have your concrete, it can also make sense to use different recipes with and without steel fibers, and also to play with the maximum aggregate size and to make layered systems. And then you can further optimize your concrete. That brings me to the end of my presentation. Here are some papers where you can find more information. But you can download these papers. They're all available, and also the PhD thesis from this website. And if you have further questions, feel free to contact me. And I have a few minutes for answering questions. Thank you.
One question.
I can hardly hear you, Tom.
Do you hear me?
Yes.
The multi-layered UHPC, I didn't know if I have catched it, but is it wet and wet or wet and dry that they are casted?
Immediately after each other.
Wet and wet. So that is also good for the bonding.
Yes. That was the background that we did it, and also for the ease of production.
Okay. Some other questions?
Same one. So.
And on the
Good. Can you check if we have any questions in the online audience?
we have this question. Can you see it, Jos?
No, I see nothing. I have to stop presenting then. Okay, what is the online question?
I can tell you. Do you consider the fibers in the particle packing optimization through the A&A model? If so, can you please on this?
No, not yet. No. So we optimize the granular skeleton, and then we add the fibers.
Okay.
Okay.
It is possible to in the model to treat the fibers also as an aggregate or as a particle, and to include it in the mix design.
Okay. Good. Well, then, if there are no other questions, then thanks a lot. You have one more, Mr. Brouwers?
Professor, did you also make fiber cocktails?
I cannot hear, sorry.
Yeah.
Okay. Professor, did you also make fiber cocktails or not?
Fiber cocktails.
Yes. So
Yes, I did not present it, but we also looked at short and long fiber combinations. So short fibers only, long fibers, and short and long together, hooked fibers, if I remember well.
And that made a difference or not?
Some difference for some properties, but I don't know by heart. You can find it in the literature, what I gave, the PhD thesis and so on.
Okay, thanks.
I think the difference was so small that in these studies that I've just shown you, we did not do it anymore. We simply took one fiber for simplicity.
Thanks.
Okay, thank you.
Good, thanks a lot.
Thank you for your attention. I have to go now.
Okay, thanks a lot. Bye-bye.